So this is going to be me going over the practice problems on the slides, right? So I'm going to go over these practice problems only. I'm not really going to go over the other content. So the question says, an orangutan weighing 500 newtons hangs from a vertical rope, and what is the tension on the rope? So if you draw a free body diagram, right, you get the force of gravity acting downward from the orangutan, and you have the tension of the monkey, of the orangutan, upward, right? So the tension is holding this orangutan upward. And we know that, well, the orangutan is at rest, so the object is in equilibrium. So we know that, well, my net force in the y direction is 0. And if we kind of look at all my forces in the y direction, well, it's t, right? Because I have a tension force upward, and I have a force through gravity force acting downward. So we have 0 is equal to t minus fg. And if we add fg to both sides, well, we get that fg is equal to t. And turns out, well, we know what fg is. It's 500 newtons. And so, because we know that fg is 500 newtons, well, we know that tension is also 500 newtons. How weird is that? How weird is that? It's crazy. So that essentially this explains it, right? So AB says draw a free body diagram of this car that's accelerating just as when you start. So if you take a look at the bolded, I mean, the only really thing you need to pay attention to is the bolded part of this question. The question says draw a visual overview and a free body diagram, essentially, for the car as it starts to move forward from rest. Now, if you read the sentence above it, it says, at high speeds, air drag is significant, but when the car is just starting to accelerate from rest, friction and drag are negligible compared to the jet thrust. So you don't really need to put it, but you can put it if you want. So if we were to draw the free body diagram, we have the force of the gravity acting downward on the floor. We have our normal force acting upward. We have our force, our thrust force, right? So we have a thrust force there, or applied force, and you have a teeny tiny frictional force, right? So that's sort of frictional force acting in the opposite direction of the motion. All right. So here, 8C, tow rope pulls a skier up a snow-covered hill at a constant speed and draw a full visual overview of the skier and include friction. So again, being pulled up the hill, right? So the skier pulled up the hill. Will represent this person. Draw different. Let's draw another person because my app is bugging out. So this is the person, right? So there's the tension force pulling the skier outward because it's being pulled by a rope, right, at constant velocity. So you know this object is in equilibrium. Right? I don't know what the hell happened. So you know this object is equilibrium. You also know that, well, there's a force through friction acting in the opposite direction because, again, this person is traveling at constant velocity, which means this person is in equilibrium. There's a force through gravity acting downward on the person. And there's a normal force acting this way. And, well, why does my normal force acting this way? Because, well, my normal force is always perpendicular to the plane of contact. And the plane of contact in this problem is the hill. Right, so that's why my normal force points that way. And again, my tension force here is equal to my force through friction because, again, the object is moving at constant speed, which means you're moving in equilibrium. You are in equilibrium. So that would be what my free body diagram would look like. So a 100 kilogram block 100 kilogram block with a weight of 980 newtons hangs on a rope. Right, so you have essentially a force due to gravity acting downward. Right, so find the tension in the rope if the block is stationary. Again, so your object is in equilibrium, which means that, well, my net force in the y direction is 0. Find the tension in the rope. So again, if your net force here is 0, well, your tension force, essentially your tension force, you have your tension minus your force due to gravity. You add force due to gravity on both sides, right? And we know, well, I'm just gonna get rid of this for now. It's gonna be 0 is equal to T minus force due to gravity, right? Because my net force is 0. I'm going to add force due to gravity on both sides. So now we have force due to gravity is equal to T, right? So Fg is equal to T. So my tension force is upward, which means that, well, if we know how much this weighs, well, 900 newtons, 980 newtons. Hold on. 980 newtons would be my tension. Okay. And then the question then goes on to say, then if it's moving upward at a steady speed of 5 meters per second. So essentially you're moving at constant velocity. You're moving at constant velocity here. So if you're also moving at constant velocity, your net force here would be 0. So we would go for the same equation, and then we do plus Fg is equal to T, and then T would be 980 newtons. All right. So that's essentially what you're doing. So again, you're going for equilibrium. So now we have this question. So what would be the correct free body diagram if the object was pulled back and then released? So at this point, this diagram is this ball is just being released. And so what would be the correct free body diagram? You definitely have a force due to gravity acting downward, right? So that would be your weight, right? So all of these would definitely already be wrong because it's acting downward in the y direction. And then you have a tension force. You have a tension force along the rope that which kind of applies a force on the ball. So you have a tension force there. And really the only diagram that kind of looks like that is B. So B is the correct one. So a car is towed. Right, a car is towed here at constant speed. So again, you know that you're in equilibrium if you're moving at constant speed, right? The problem say so. Which means that, well, if I have a tension force this way, and it's moving at a constant speed, well, we have to know, well, there's a force due to friction there, right? My forces add up to 0, so my force due to friction is equal to my tension force. And so there's a force due to friction there, and so then there's also a force due to gravity acting downward, right? And then there's a normal force acting upward, right? So there's a normal force acting upward. And that would be my free body diagram. And my normal force would also equal to my force due to gravity because, again, all the forces acting in the y direction would have to equal to 0. So all my forces acting in the y direction are my normal force minus my force due to gravity. And if you get 0 is equal to Fn minus Fg, well, we know that Fg is equal to Fn, right? Same magnitude. Okay.